Our today's topic is Lenz's law. Where do we apply Lenz's law? Lenz's law we apply where we are applying Faraday's law of electromagnetism. Faraday's law of electromagnetism, we apply Faraday's law of electromagnetic induction. Here is a coil and we are changing magnetic flux linked to this coil. How do we change the magnetic flux linked to this coil? There may be many methods, but we are not going to the methods. What happens when we change? Here is a magnet. Let us say it has got North Pole on this side, and from here the magnetic field is strongest here, it is weaker here, it is again weaker here. So this way magnetic field change. This change we express by magnetic field of lines. Here the concentration is more and here the concentration is less. So nearer the lines, stronger is the magnetic field. Okay. Now this is representing strength of magnetic field, the distance. Now when we bring it closer to it, what is the effect on magnetic flux linked with this coil? Now the answer is the magnetic flux linked to this coil will change and it will become more. This will come here, and when it comes here, then we will find it is north and like this. The magnetic flux link become larger, more, and this induces current here. That was Faraday's explanation, and that is what Faraday said. It will make an EMF is induced in it. And what does an EMF do? An EMF starts current if the circuit is closed. Like we have a cell. In the cell there are two terminals, one is plus, one is minus, and this has got EMF between the two. If we make a circuit here and close this circuit, if we close this circuit, then what will happen? The current will flow from plus to minus. So EMF is the source of electric current. Here when we bring it nearer, the magnetic flux increase and EMF is induced in it, and because of that EMF, if circuit is closed, then the current will start flowing in this. Okay, that is Faraday's law. We have already done it. Then what is Lenz's law? Lenz's law tells us whether the direction of current will be in this direction or whether the current direction will be in this direction. So Lenz's law speaks only about this, the direction of electric current. Okay. Now, what is the Lenz's law? The Lenz's law says that the direction of electric current will be such that it will oppose the change in flux. In physics, we have studied, we have read a very basic fundamental rule, and that rule says that nature always try to resist any change. And all our physical activities, all our laws, all our phenomena are based on this. That there is always an opposition to the change. Now here, when this was here, the flux linked with the coil was only 1. When it comes here, the flux link becomes 5. Earlier it was 1, when it comes closer, it becomes 5. Coil does not like it. Then what it will do? It will make a flux. And that flux will be in opposite direction. And how much will be the quantity? You can very well guess it. The quantity will be 4. It was earlier 1, it has made it 5, it will create 4 so that it will remain for 1, which was earlier. It is trying to make it 1. But the thing is, how a coil can make a magnetic flux? The answer is magnetic flux is made by flow of current in a coil. And how the current flows in a coil? The current flows in a coil with help of electrons. And this coil, every coil has plenty of electrons because it is made of conductors. So the electrons flow in it, that means current flows in it. Now that current flows in it and that opposes this change. ये जो 1 से 5 हो रहा है, इसको ये अपोज करने का क्या तरीका निकालती है? ये 4 फ्लक्स उल्टा बनाती है. जब ये 4 फ्लक्स उल्टा बनाएगी तो फ्लक्स कितना बचेगा? 1. That is what it want. तो इसलिए उल्टा फ्लक्स बनाने के लिए ये अपने में करंट फ्लो कराएगी. Now, what should be the direction of that current? That we have to see only in Lenz's law. Now, the flux direction will be this induced flux in this direction. Now we have to see our rules how a flux will be made in this direction, and we know by right hand screw rule, if we have to make the flux here, the current should be like this way. So this will be the direction of current, electric current. So the flux is made on this direction. When this will be direction of current, the flux will be made in this direction, and that will try to cancel out the increase. जितना ये बढ़ रहा है उसको कैंसल करने के लिए इसने फ्लक्स बनाया, और इस फ्लक्स के लिए इसको करंट ऐसी फ्लो करानी पड़ेगी. So this will be the direction of current. This is what Lenz's law says. So this is now going closer this way. Suppose we make it opposite case. Here is the coil and here is a magnet, and we are moving the magnet opposite direction away from the coil. Here the flux is very large connected to the coil. When we move it away, then what will happen? The flux will become less. If the flux will become less, then the coil would like to oppose the change. How the coil would oppose the change? Answer is the coil will generate more flux in this direction. How coil will make more flux in this direction? By flowing current in itself. How much, in which direction should it flow? Again, we go by the right hand rule. We want flux. The coil wants flux in this direction because it is reducing. It wants to supplement it. उसको उसमें ज्यादा करना है, ऐसा फ्लक्स बनाना है, तो वो करंट ऐसे बनाएगी. Right hand screw rule. So if this is the flux required, this is the magnetic field required, then this will be the direction of current. So this will be the direction of current in this way if we are moving the magnet in this direction. Now you see, if we move the direction in this way, then this is the direction of current. If we move it this way, then this is direction of current. And with these, what is our ultimate result? What is Lenz's law? That the direction of current will be such that it will oppose the change in flux. That's all. So let's write Lenz's law. The direction of induced current in a coil is such that it will oppose the change in magnetic flux. This is Lenz's law. Okay. So this is Lenz's law. Now let us study it a bit more. How do we remember it? We remember it when the north is going closer. It will oppose. Why the flux is changing? The flux is changing because north is coming close, and the coil will want that north should not come close. If north should not come close, then what it can do? It can produce a north pole in itself, so that this north will repel this north. Now how a north pole is induced in the coil? By this type of current, because north pole always gives out magnetic flux. So we remember it this way. This is the coil and this produces a north pole. This. So we remember it is anti-clockwise. Anti-clock. If the current is anti-clock, then what is the direction of magnetic pole? We observe this is north pole. When the north pole is induced, when this north is coming closer. Now, if this north is moving away, this case, if the north is moving away, then the coil wants that it should not move away, so this will make a south pole. How this will make a south pole? South pole, what happens in the south pole with respect to magnetic field? The magnetic field enters the south pole, so magnetic field enters the south pole and the current will be this way, that is clockwise. So we remember it this way. This is the coil. If the current is clockwise, this will make a south pole, and let us put arrows here. So this type of current makes a south pole and this current makes a north pole. So this we will remember, and this is Lenz's law. Now one very important thing comes from here. If a charge is making a circle, I see it from this side, the charge is making a circle, I will say that this is north, because I know this way it will be north. Now if I see it from the other side, then it will appear to be south. But when I see it from this side, then the current will be in opposite direction. Here if I see the current is flowing like this, and I say it makes north pole. If I see it from this side, then the current will be this, and this will make south pole. Now there is only one charged particle, only one circle it is making. From here I say it is north pole, from here I say it is making a south pole. So is it making a north pole or the south pole? The answer is, here is the basic answer, that there is only one particle making the circle and it is making both. North pole if you observe from one side and south pole if you observe from the other side, and this gives the very important fact that north and south cannot be separated. If you remove this particle, north and south both are gone. If you move this particle, north and south both are there. And that is why in a magnet there has to be north pole and south pole altogether. Similarly, the magnetic field will come out from north and it will go to south. So if this side is north, then north it will come out and come back to south. It is a complete cycle. There is no end to it. Okay. Now this is again, we come back to the Lenz's law. This is the Lenz's law. Now there are one or two very important things in Lenz's law. The Lenz's law is a very small thing in this chapter, but the question when comes, it really confuses the student a lot. Now I will tell you what type of questions are there which makes a lot of confusion to the students. Here is a coil and we are bringing this north pole in this direction. Now we use our knowledge that this is going to make north pole, and therefore current will be in this direction. This is the direction of current, so the north pole is there and this will make a north pole. Okay? This is direction of current. Right? Now if we ask you that if we make this coil like this and there are two terminals and we have not completed the circuit, will there be current? Answer, there will be no current, because for the current the most required thing is completion of the path, completion of the circuit. Now there is no completion of the circuit, so there will be no current. Okay? There is no current, then will there be EMF? Answer is yes. Because the Faraday's law says whenever there is change in flux, there will be an induced EMF. It does not say there is induced current. There is induced EMF, and if the circuit is completed, then there will be current. That means if we complete this circuit here and we put a bulb here, then there will be current flowing in it. Okay, then this will be the direction of the current and it will flow like this. Sorry, this way, and this will go this way. This is the current flow in it. Okay, so if it is not completed, what will happen? This is the question which is sometimes asked, and what you have to say. There will be EMF between these 2 points. Okay, that's right. Let's give them name A and B. The question is, out of A and B, which is positive terminal and which is negative terminal? This is very important question and most of the students get confused in it. किसको plus बोलना है, किसको minus बोलना है? And what do they remember? The current flows from plus to minus, and here is the current flowing. The current is flowing from plus to minus, so B must be plus, A must be minus. And here they make the mistake. It's not like that. Now what I want to tell you, see the example of the cell. In cell, this is plus, this is minus. Current flows from plus to minus, and what is happening inside the cell? Inside the cell, current is flowing from minus to plus. So this is same amount of current, I. This is also I. So what is the direction of current? Is it minus to plus or is it plus to minus? What will be your answer? Yes, the answer varies. What we remember here, we make a fixed rule, it's very clear. This is source of EMF. In the source of EMF, inside the source of EMF, the current or the energy goes from minus to plus. Outside the source, it goes from plus to minus. So the essence in your answer is inside the source, outside the source. Remember, outside the source of EMF, EMF source. This may be a cell, a battery, a generator, or anything. So the current goes from one terminal to the other, that is plus to minus, but this is outside. Outside the source, and this is inside the source. Okay, so we remember this rule. Inside the source, minus to plus, outside the source, plus to minus, and come back to this. Here, how the current will flow. It is given to us that the current is flowing like this, then whether B is positive or negative. So you have to think whether it is inside the source or is it outside the source. The answer is this coil has, if we connect this coil here, then the current flow. Why the current is flowing? Because it is connected with this coil. That means who is the source? The coil is the source of energy. If the coil is source of energy, it gives current to it and the current is flowing here. If this is source of energy and this is the user of energy, the current is flowing in it and the current flows from plus to minus and the current flows from A to B. Then what is the sign of A? Plus, and what is sign of B? Minus. So the current goes from A to B, that is from plus to minus. So this becomes minus. Okay, if you see this very well, you can very well see this and it is correct because inside the source it goes from minus to plus. This is inside the source. Inside. And inside the source it goes from minus to plus. So this is how you will decide polarity of the 2 points. This is again required. This is again required very much when you have the questions like this. There is a magnetic field B. This magnetic field is going inside the board. And there is a rod here. This rod is falling down. This is velocity. So, and we know by Faraday's law, an induced EMF will be there between the two ends A and B. Okay, now we apply our rule. What is that rule? Right hand rule. This 90, 90, 90. This shows magnetic field. So this is magnetic field inside, and what does this show? Velocity. So this is velocity. This is magnetic field, this is velocity, and this is direction of current. If this is direction of current, but will there be a current? There is no circuit completed. So there will be no current. If we complete the circuit somewhere here, like this, then there will be current in this way. Suppose there is no circuit like this and it is disconnected, the switch is off, then A and B, there is no current. Do they have a potential difference? Answer is yes, they do have a potential difference. If they have a potential difference, then which is plus and which is minus? Again, now if this is falling down, which is plus, which is minus, for this students are again confused thoroughly, but take this formula. This is a source of current. If there is a source of current and we connect a bulb, this bulb will glow. The current will start from here and the current will end here. Now, if the current starts from here, what is this? This is plus. And what is this? This is minus. This makes you very clear if this is source. The direction of current is from minus to plus inside the source, and if we connect it with the outside user, then it will be from plus to minus, and if we don't connect it, then there will only be potential difference. EMF will be there, but there will be no current. So remember the rule of polarity in this way. The questions are asked in this way, and now again these questions are made little more complicated. How? If this is falling down, then we find that in A and B, one of the point, either A or B, has more electrons and the other has less electrons. Now which point has more electron and which point has less electron? You have just seen. From our knowledge, we have now got that B has to be positive because the current outside coming from B, it is going out. So B is positive and A is negative. This makes it very clear that A has got more electrons and B has got less electrons, and it is positive. It has excess of electron, so it is negative. So it has got more electron. We can make it a bit more complicated. The question will come, if this rod is exactly balanced here, it is falling down, then which side the weight will be more? The answer is on A side weight will be more because all electrons are accumulating on A side. The electrons from here comes to this side. So this becomes more in weight. Okay, so this should solve all your confusion and make it very clear. V will be positive and current will flow in this way. So this is we could find from Lenz's law. Lenz's law is also connected with another very important principle which give birth to Lenz's law, and that is conservation of energy. That is a fundamental principle. How Lenz's law is connected with fundamental law of conservation of energy? Conservation of energy applies everywhere, so here it should also apply. When we have a coil here and we are bringing this closer to the coil, current flow in it. If it is coming in this direction, this will make in this direction and there will be current in this direction. Okay. This is the current flowing. Conservation of energy. Remember, there are many things which tells us the calculation of energy. The current flowing in a coil needs work to be done. I square R or V into I. Those are the formulas for work done per second. So if the current is flowing in it, then some work is being done in this. Now, if work is being done, then somebody must be spending energy. That is why the work is done. Who is spending energy? Which energy is being transferred here as a work done? And this work done is how much? I square into R, where R is resistance of the coil and I is the current flowing in the coil. Now I square R, this work is done here, which is radiated away as a heat. But from where does it come? The answer is it comes from, no, not from the magnet. It comes from that agent, that person who is moving the magnet. He is doing the work. So, a person who is moving the magnet, the agent who is moving the magnet, he is spending his energy, he is doing the work on magnet, that work in motion, because he applies force, gives the displacement, that is the work done, that work done comes here, transferred to the coil. So, the energy of the person, energy of the agent decrease, energy of the coil increase. That energy, now the sum is again balanced and that energy is transferred. This energy is again transferred in the form of heat and that heat is radiated out in the atmosphere. This is conservation of energy. Now another thing, we can understand Lenz's law with conservation of energy. How? If this is making magnetic field 1, if it comes closer, the magnetic field become 5 lines. Now, this has to produce a magnetic field. We cannot see it with the eyes in which direction it will make magnetic field, but we can assume. How we can assume? That if it is either making magnetic field in this direction or it is magnetic field in this direction. If we are pushing it on this side, this is the direction of magnetic field. If it also makes magnetic field in this side, then this magnetic field increase as positive work. Suppose then this coil is also doing a positive work. The total work done is W and W, 2W. This is not possible because our conservation law says the energy given to one body is equal to the energy lost by the other body. So if this body is doing a positive work, this body has to do a negative work. And if the going of magnetic flux in this direction is positive, then making the magnetic flux in this direction should be negative. Therefore, it does not make magnetic flux in this direction, it will make a magnetic flux in this direction. So there is a plus work done, there is a minus work done, they cancel each other, and this is why we concluded. इससे हमने फैसला क्या किया कि इसका मैग्नेटिक फ्लक्स किधर बनना चाहिए, इधर बनना चाहिए. So this conservation of energy is explained in Lenz's law. Conservation of energy is explained in Lenz's law. Lenz's law. It's a very small chapter, but it makes your understanding very clear. What should be the direction of EMF, how you will find the direction of current, and what is the reason, and how the energy is conserved. If they are on the same direction, it is not conserved. Some energy is gained. That is not possible. We cannot create energy. So if there has to be a positive work done, there has to be a negative work done. Therefore, Lenz's law proves the conservation of energy. It is according to conservation of energy. So this was Lenz's law. Thank you.